And now it's time to pass!
Can you see my screen?
मेरे संगीत
Yes, sir.
yes बढ़िया है सर.
Okay, so now we can start this partial derivatives. So for partial derivative, let us consider x naught, y naught is a point inside the domain of a function. And so in the graph, you can see that this point is x naught, y naught. So if I take y is equal to y naught, this plane will cut the surface, which is z is equal to fxy, in the curve z is equal to fxy naught. So you can see that we have the y-axis here and the x-axis. On the y-axis, you take y naught, and corresponding to this, you will have a plane like this. You can see that we have a plane here. Fine. So this plane will cut the surface to give us a curve. So this is the curve we have. Okay, so you have y is equal to y naught here, and corresponding to this, you erect a plane at this point, and this plane will cut the surface in a curve. So you get this curve. Fine. Now the slope of the curve. Can you mute yourself? The slope of the curve at the point x is equal to x naught is known as partial derivative with respect to x at point x naught y naught. Okay. Right. So that means to calculate the partial derivative of a function of two variable x and y at a point x naught y naught, to calculate the partial derivative, we fix the value of y at, say, y is equal to y naught, and by fixing this y, we are geometrically erecting a plane in the at y is equal to y naught. This plane will cut the surface to give a curve, right? So this curve will be a function of just one variable, the variable x. And then you know how to calculate the derivative of a function of one variable. This will be the partial derivative with respect to the variable x at point x naught y naught. Okay. Similarly, instead of fixing the value of y, if I fix the value of x, let's say x naught. So we have this x-axis. So at this point, we fix x is equal to x naught. When we fix x is equal to x naught, we get a surface, which is this surface. And this surface will cut, this plane. This plane will cut the surface in a curve, and this will be the curve. Okay, so this curve is a function of just one variable, the variable y. And then you calculate the derivative with respect to this variable y using the notion of derivative for a function of one variable. Okay, so this is known as partial derivative with respect to y. Okay, so that means in order to calculate the partial derivative with respect to x, we fix the variable y to make it a function of one variable, and then differentiate it as if it is a function of one variable with respect to x. To calculate the partial derivative of the function with respect to the variable y, we fix the value of x. By fixing the value of x, this will become a function of single variable y, and you differentiate this with respect to y in the usual way. That gives you the partial derivative with respect to the variable y. Okay, so geometrically, geometric interpretation also we have seen just now. So this is the geometric interpretation of the partial derivative with respect to x. This is geometric interpretation of partial derivative with respect to y. Okay. So now we can mathematically define partial derivative. This is the definition of the partial derivative. So we said that for partial derivative with respect to x, we fix the value of y. So y is fixed at y is equal to y naught. This is fixed. Okay. Now by fixing this function will become a function of just one variable. Okay. Function of one variable, and then you differentiate this function with respect to x. So this is the notation that we use for the partial derivative of f with respect to x. Okay. So that means the usual way to define the derivative, the left-hand derivative and the right-hand derivative. This will be the definition. So here the value of y is fixed. This is fixed. And value of x is changed from x naught to x naught plus delta x. Delta x can be a positive number. It can be a negative number. So if delta x is positive, and you take the limit delta x goes to 0, then you are calculating the right-hand derivative. If delta x is negative and taking delta x goes to 0, you are calculating the left-hand derivative because you are approaching from the left-hand point, left-hand side of the point. Okay, so this is the definition of the partial derivative with respect to x. And similarly, the definition of partial derivative with respect to y, you can define this as you can define this as this. You fix the value of x, so this is x naught, and change the value of y from y naught to y naught plus delta. Okay, and then take delta y goes to 0. Okay.
Sir, provided limit exists means this
Finite.
limit or limit x naught y naught.
This limit should be finite. If it is infinite, then or the limit does not exist. So you see that we have seen the definition of the limit, right? And we have seen that to show that the limit exists, we have to come from all directions. And to show that the limit does not exist, you also show that there are two directions which lead to different limits. Okay. So since in this case we have fixed one variable, in the first definition we have fixed the variable y. So I have a function of only one variable, right? So to approach x naught, I have only two directions, left hand side and the right hand side, right? So in that way. So basically we are saying that left hand derivative and the right hand derivative are equal and finite.
Yes, sir.
Okay.
Yes.
Okay, so now let us see that it is clear from the definition that the partial derivative of f with respect to the variable x can be calculated by differentiating f with respect to x in the usual way by treating y as constant. As I said, you fix the variable y for partial derivative with respect to x. And similarly, the partial derivative of f with respect to the variable y, we differentiate with f with respect to y by treating x as a constant. Okay, so in that way you can calculate the partial derivatives. So we have this example. fxy is equal to x square plus 2xy plus y minus 1. So you want to calculate the partial derivative of f with respect to x. So how are we going to do this? As I said, when you calculate partial derivative of f with respect to x, you treat the variable y as constant. So first element on the right hand in this function is x square. So derivative of x square is 2x. Then the second element is 2xy, and you have to treat y as constant. So when y is constant, the derivative of this will be 2y. Third element is y. Y is constant, so derivative of a constant is 0, right? And then minus 1. 1 is constant, so derivative of constant is 0. So partial derivative of this function will be this one, and you calculate this at the point 1, 2. So that means the partial derivative of f with respect to x at point 1, 2 will be substitute the value of x is 2 and y is 2 into 2. So it will be 6. So this is 6. Okay. Similarly, if you calculate the partial derivative of this function with respect to the variable y, this will be, the first term is x square. It does not depend on y. And for partial derivative with respect to y, you have to treat the variable x as constant. So x square will be constant. Derivative of this will be 0. Okay. Second element is 2xy. Here x is constant. So derivative of this will be 2x. Third element is y. So derivative of y will be 1. And last element is minus 1. So derivative of this will be 0. So you get 2x plus 1. And then evaluate this at point 1, 2. So put x is equal to 1. So this will be 2 into 1 plus 1. And y is 2. There is no y here. So this will be equal to 3. Okay.
Sir, why are partial derivatives used?
Just like the derivative, it is you have to, if you look at the geometric interpretation, this gives you the slope of the curve that you obtain hereby. So this gives you the slope here. Okay. So in practical applications, you can think of a situation where you have a function, right?
Yes, sir.
Okay. So now let us calculate, let us see this example also. You have this function and you want to calculate the partial derivative of this with respect to x. So partially y is constant, so you just write we are calculating the partial derivative with respect to x. So you treat y as constant, derivative of, and then apply this chain rule. So you consider this as a function of just one variable. Okay, you apply the chain rule for function of one variable. So derivative of sine will be cos x by xy by 3, and then derivative of xy by 3 with respect to x. Y is constant, so y by 3 will be out, and derivative of x will be 1, so it will be y by 3. So you write y by 3 here. Okay. So this will be equal to y square cos xy by 3. Okay, so you get this one. Fine. Now you calculate the partial derivative of f with respect to y. So here you see that you have a function of y here and you have a function of y here. So you have product of two functions. So you can apply the usual product rule. The product rule for the single variable. So you have first differentiate 3y with respect to y. This gives you 3. Then multiply sine xy by 3. Then you have this 3y, and the derivative of sine will be cos. Apply the chain rule here. So cos xy by 3, and derivative with respect to y. So change for chain rule, you have to differentiate xy by 3 with respect to y. So this derivative will be x by 3. Okay. So you get 3 into sine x y by 3, and from here you get The second term will be 3 cancels out, so you get xy into cos xy by 3. Okay, so this is how you calculate these partial derivatives. Any questions so far? Any question? So now you have this example. The plane x is equal to y intersects the paraboloid z is equal to x square plus y square in a parabola. Okay. Obtain the slope of a tangent at the parabola at the point 2, 1, 5. Okay.
Sir, if there are 3 variables and I need to check for one variable, keeping the I need to check for 2 variables. So how can we take a derivative for 2 variables at once?
So this is a function of just 2 variable. There is no three variable. This is a function of 2 variable.
Yes, sir. I was asking for some other type.
You mean the extension?
Yes, yes.
Yeah, extension, you can extend this definition in the same way. For example, you can input more variables here. Let's say if you have a function of x3 variables, x1, x2, x3. So derivative with respect to x1 means you keep 2 variables x2 and x3 constant and treat this as a function of just one variable x1 and do the derivative in the usual way for function of one variable. And similarly, partial derivative with respect to x2 and x3.
Sir, if I need to take a partial derivative with both x1 and x2 at once, then
No. So then you have to go to the definition of derivative. So if you have f, x, y, and z, and you are saying that you will keep this as constant,
yes,
and then you want to change x, y to x plus delta x and y plus delta y, and you want to look at the simultaneous change in f when x and y are simultaneously changed. Okay, so that will require the notion of derivative, not the notion of partial derivative of f, where f is a function of 2 variables.
yes, sir. So that derivative rule will be
So derivative that will come later. So after partial derivative, we will go to derivative of function of 2 variables.
okay, sir.
Because whenever you say that I will change x and y simultaneously, then you are basically creating a neighborhood around the point x and y, and then you are coming from all possible directions. Okay, so this notion is completely different from the notion of partial derivative. In partial derivative, you fix all variables except one variable. If you have a function of 2 variables, you fix one variable. If you have a function of 3 variables, you fix 2 variables and treat this as a function of one variable. If you have a function of 4 variables, you fix 3 variables and treat this as a function of one variable. So notion of partial derivative is different. The notion that you are asking, or the question that you are asking is about the derivative of a function of 2 variables. That we will see later.
Okay, sir.
Okay, so it is like because for a function of 2 variables, you have to come from all possible directions, just like the limit and the continuity that we have seen. So the definition has to be given in that way, so that when you come from all possible directions, the notion of derivative can be defined. Okay.
Okay, sir.
Yeah. So I leave this example for you to do because this is just calculating the partial derivative here. Basically, you have this function. When you differentiate this with respect to x or with respect to y, you get 2y. Derivative with respect to x will be 2x, and then evaluate at these points. Okay, so I leave this for you to do. Now we try to extend the notion of a function of more than two variables. So I have variables x1, x2, xn. This is a function of n variables. And I have x1 tilde, x2 tilde, xn tilde be a point inside the domain D. Okay. Then the partial derivative of f with respect to xi at the point x1 tilde, x2 tilde, xn tilde is defined as, so this is the partial derivative, this is defined as you fix all variables except the ith variable. So this is partial derivative with respect to the ith variable. You see in the suffix of f is xi. So if I write fxi, this means I'm calculating the partial derivative with respect to xi. So when you calculate partial derivative with respect to xi, you have n variables here, x1, x2, xn. Except xi, you fix all other variables. Okay. So I variables except xi, x1 tilde, x2 tilde, so on to xi tilde, xi minus 1 tilde, xi plus 1 tilde, xn tilde. These variables are fixed. And the ith variable is changed. Ith variable is changed from xi tilde to xi tilde plus delta xi. Okay. And then you take the limit. So basically this becomes a function of just one variable, xi, when other variables are fixed. So you do the derivative as if it is a function of just one variable. Okay, so this is how it can be generalized.
Sir, can we define simultaneous based on partial? Like if there are n variables, I differentiate with respect to one every time, and then I sum the squares of all of these and take the square root, like under root x square plus y square sort of.
No. So when you take this, when you fixed, for example, so this notion of limit will change because when you have two variables, you have this change xi. For example, if you have three variables, right? X,
Yes.
y, and z, and you fix this z. Okay, so in the limit definition, when you put this limit, this is change in x, delta x, this is change in y, delta y. This goes to 0. So this notion, and you write this difference here. So this notion is defined only when you come from all possible directions. So this is a completely different definition, which is the definition of differentiability of a function.
So
Fine?
sir, first differentiating with x, then with y gives wrong.
Yeah, because every time you differentiate with respect to x, other variables are fixed. This is not wrong. This notion is different from this one. Just like the iterated limit you had. You fix one variable, take the limit, and then change the other variable. So iterated limit is not limit. So here also, you differentiate with respect to x, and then differentiate again with respect to x. This will be a different notion.
Yes, sir, because all other parts are not included.
Yeah, so this is second order partial derivative and something like that.
Okay, sir.
Okay. So there are several things going on here. The best way to identify the difference is to look at how the limits are taken. If you are taking the limits only for the one variable by fixing other variables, by fixing other variables, then this means that you are calculating partial derivatives. Okay, you see that this limit is only with respect to one variable. Okay, fine. So you are coming only from one direction. You are not coming from all direction.
Yes, sir.
So this is how you identify. So later you will see that we have the notion of derivative where we will come from all possible directions. So find the partial derivatives of this. So again, this is also a very simple exercise. You just partial derivative with respect to x means you have to keep y and z as constant. So that means sine y plus 2z will be constant, and differentiate derivative with respect to x will be just derivative of this. So you get this one. And similarly for the other variables, derivative with respect to y means x and z are constant. So when x and z are constant, you have x, derivative of sine will be cos y plus 2z, and z is constant. So when you use chain rule, you get derivative of y as 1. Okay, and similarly derivative with respect to z will be x cos y plus 2z, derivative of y plus 2z will be 2. So you have this 2x here. Okay, so this is an example where we have a function of 3 variables. Fine. And some homework here, so you can try these questions. Now, continuity and partial derivatives. So if I say, let us consider a function of one variable, okay? And if I say that the function is differentiable, can you say that the function is continuous? Yes or no?
Yes, sir.
Yes. Now, if I say that the function has partial derivatives, can we say that the function is continuous? Now
No,
consider a function of two variables. No, the answer is no. So if you have a function of two variables and the partial derivative exists, this does not mean that the function is continuous. And the reason is clear from the definition itself. When you talk about continuity of a function, you come to the point x naught, y naught from all possible directions, infinite number of directions. When you calculate partial derivatives with respect to x, you fix the value of y, and then you change you approach only from two, because once y is fixed, you have a function of just one variable, and for function of one variable, if you differentiate, you come from only two directions, left hand side and the right hand side. Okay, so from the definition itself, it is clear that there is no relationship between continuity and partial derivatives. Okay, so here I'm giving some examples where this is illustrated. So you have, let's say f is equal to this one. Whenever x square plus y square is not equal to 0, f00 is equal to 0. You can calculate the partial derivative of this function at x0, at point x0. So when that means y is 0, so you put y is equal to 0 here, right? And x is not 0, let's say. So when x is not 0, y is 0, that means x square plus 0 square is not 0. So when y is 0, clearly the function is 0 when you take y is equal to 0 here. And derivative of 0 will be 0, so you get 0. Similarly, if you want to calculate the partial derivative, of this with respect to y at point 0 and y, you put x is equal to 0 here, function becomes 0, and you get the derivative as 0. Okay, so you see that both the partial derivatives exist for this function. And similarly, you can calculate the partial derivative at point 0y. So you take this will come out to be minus y, and this will come out to be x. So you have the partial derivatives, but the function is not continuous at 0, 0. Okay, right. Similarly, in the second example, one can check that the partial derivative exists at point 0, 0, but the function is not continuous. Okay, and the third example, again, you can see that the function is continuous. Though the function is continuous, but the partial derivative does not exist. Okay, so there is no relationship between partial derivatives and continuity of a function of two variables. Okay, so these examples are given to illustrate this. Fine. So this is explained here with another example. So consider for a function of one variable, existence of its derivative implies continuity of the function. But for a function of two or more variables, existence of its partial derivatives does not imply continuity of the function. For example, if I consider this function, xy is not equal to 0, the value of the function is 0, and xy is equal to 0, the value of the function is 1. This function is not continuous. And this is clear from the definition itself. At point 0, 0, the value of the function is 1. Okay. If you take any other point, 0, delta x, then delta x, any other point, delta x, delta y, the value of the function is 0. And when you take the limit delta x, delta y goes to 0, this limit will come out to be 0. Okay. So the limit exists, which is 0, but the limit is not equal to the value of the function, which is 1. Therefore, function is not continuous at point 0, 0. Okay. Now, can we say that the partial derivative exists? And here we can see that the partial derivatives exist at 0, 0. Okay, so for partial derivatives at 0, 0 with respect to x, we want to calculate partial derivative with respect to x at point 0, 0. So we put y is equal to 0. So take y is equal to 0. This value is fixed. This value of y is fixed. And then change the value of x from 0 to delta x. Okay, using the definition. So this is the value here. At 0, 0, the value of the function is 0. And at this point, also the value of the function is 0. So the difference is 0. You take the limit, delta goes to 0, the limit will be 0. So that means the partial derivative exists. Okay. If you take the partial derivative with respect to y, so I'll keep x as constant. So I keep x as 0, x at 0. And so when x is 0, this product is is 0. So the value of the function will be again 1. This will be 1 minus 1 divided by 0. So this is 0. Limit will be 0. So this partial derivative also exists. Partial derivative with respect to y also exists. Okay, so both the partial derivative exist, but the function is not continuous. Is it okay? Any question? Okay, so no questions, so we move further. Now we give the sufficient condition for continuity. So it says that if one of the partial derivatives exists and is bounded in the neighborhood of the point x0, y0, and the other partial derivatives exist, then f is continuous. Okay. So in the previous examples, we have seen that if the function is continuous, this does not mean that the partial derivative will exist. And vice versa also, if the function has partial derivatives, this does not mean that the function is continuous. So in this theorem, we are answering under what conditions the function will be continuous. So it says that if the function has partial derivatives and one of the partial derivative is bounded, then the function is continuous. So you can calculate the partial derivatives at point x0, y0 and check with if one of the partial derivative is bounded, then you can say that the function is continuous. Okay, so this is the proof is given here. We can check this. We can check this condition here. So I leave this proof for you to do. The reason is that proof is not going to be part of the evaluation. However, for your understanding, you can read the proof. In case you find it, if in case you find any difficulty in understanding the proof, you can give me a call. Okay, anytime you can give me a call and we can discuss it. Okay, but based on this result, we will consider one example. Based on this result, we consider one example. So we have this function fxy is equal to xy square divided by x square plus y square. Any question?
Sir, but in that proof, sir, how if one of them exits the neighborhood, sir, but then we have not checked all the parts for continuity.
So neighborhood is coming from this, is bounded in the neighborhood of the point. So at intuitive level, it says that when you come from all possible directions in the neighborhood of the point x0, y0, the partial derivative does not blow up, does not go to infinity. Okay, it remains bounded. So somehow there is a control on the function in the neighborhood of the point x0, y0. And with this intuition, one can imagine that the function may be continuous. Okay, and it will turn out to be that the function is indeed continuous. Right.
Okay.
So this means that if you want to find a sufficient condition for continuity of the function, you must impose at least one properties in the neighborhood of the function. Okay, so this condition is boundedness in the neighborhood of the around the point x0, y0.
Sir, other partial derivative exists means it has increased out of the boundary.
Exist. This is typing mistake. S is missing. Sorry
Okay.
about this. No, it doesn't go out of the boundary. Otherwise, nothing you can claim.
Yes, sir. Okay.
Okay. Nice observation, and thank you for the correction. All right. So here you can calculate the partial derivative at 0.00 with respect to x. So at 0.00, the value of y is 0. So you put the value of y, which is 0 square, and x is changed to x0 plus delta. So x will be 0 plus delta. Okay, fine. And the value of the function at 0.00 is 0. So you have 0. Okay, so this limit delta x goes to 0 will be 0. Okay. Similarly, when you calculate the partial derivative of the function f at 0, 0, you substitute the value x is equal to 0 here, and the first will be, you just go back to the definition. I'm just using the definition of partial derivatives. So you just look at the definition here. If anyone has any confusion what I'm doing here, so you just look at the definition. So the point is 0, 0, x0 is 0, and y0 is 0. So just substitute x0 0. So this will be 0 delta y, and this will be 0 0. Okay, so this is what is written here, the value of the function here. Okay, and when you take this limit will come out to be 0. Right. Now both the partial derivatives exist at this point. Now we have to check the other condition. You have to check the other condition here, that what is the condition. So first condition we have checked, the partial derivative exists, other partial derivative also exist, and one of the partial derivatives should be bounded in the neighborhood of the point x0, y0. So in this case the point is 0, 0, so we check the boundedness of the partial derivative in the neighborhood of the point 0, 0. Okay, so when x and y is not 0, so that means x and y is coming from the neighborhood of the point 0, 0. Then you calculate the partial derivative of this function with respect to x by treating y as constant. So you apply this. So you can calculate this derivative. So this derivative, you have x derivative of the numerator with respect to x, which will be y square times x square plus y square minus x y square, and the derivative of this with respect to denominator will be 2x with respect to x, and x square plus y square whole square. So basically, when you calculate the partial derivative with respect to x, you treat y as constant and differentiate this with respect to x. Okay. So you will get, after solving this, you get this will solve to this quantity. Fine. And now we can check that this partial derivative is bounded. So fxy is equal to this one. So you can take y square divided by x square plus y square outside. This quantity is bounded by 1. And the other one is y square minus x square divided by x square plus y square. So that is also bounded by 1. This quantity is also bounded by 1. Okay. So both the quantities are bounded by 1. So product is also bounded by 1. So we can say that this is bounded by 1. So that means the partial derivative with respect to x is bounded in every neighborhood of the point 0, 0. Both the partial derivatives exist. That means the function is continuous using this theorem. Fine.
So what have you calculated above this, the fx 0, 0, 0?
Sorry, what I have calculated here? Which one?
Sir, above this statement for here fx 0, 0 equals to.
This is partial derivative of f with respect to x.
Yes, sir. Can you explain this, how this came out to be this?
So let's go back to the definition of partial derivative with respect to x. So this is partial derivative with respect to x. This is the definition.
Yes, sir.
And our point is, in this example, x naught, y naught is 0, 0. Okay?
Yes, sir.
Right. So what do you get here? If I take this at point 0, 0, so this will be limit delta x goes to 0, f 0 plus delta x 0 minus f 0, 0 divided by delta x, right? And delta x is approaching towards 0. This is how this limit is defined. This means that delta x is not 0, right?
Yes, sir.
So identify the value of the function in the given example, value of the function at point delta x and 0. So what is that value in this example?
Okay, sir. We'll put delta x. Okay.
Okay, so that value is this one. And the other one, is f0, 0. So value of the function at 0, 0. Value of the function at 0, 0 is 0. You see that this definition is 0. Okay.
Yes, sir. Got it.
Is it clear?
Yes, sir.
Right. This is how you calculate the partial derivatives. Any questions so far? If no, we can move to the higher order partial derivatives. Any more question? If no questions, so we move to the higher order partial derivatives. Now, This is also very straightforward generalization. So if you have a function of two variable, and if I ask you to calculate the partial derivative of this function with respect to the variable x, so you will fix the value of y. This will make this function as a function of single variable. Okay, and then you calculate the partial derivative with respect to x. So this function can be differentiated because this is a function of just one variable x. So you can differentiate this function as many times as you wish. So if you differentiate this function with just one times, you get the partial derivative with respect to x. If you differentiate this two times, you get the partial derivative, second order partial derivative with respect to x. If you differentiate this three times, you get third order partial derivatives with respect to x. Okay. Similarly, if you treat this as similarly, if you fix the variable x and treat this as a function of variable y, and then you can differentiate this function as many times as you wish. So first derivative will give you the partial derivative with respect to the variable y, and the second order partial derivative with respect to the variable y. Okay. Now there are some other types of derivatives also. These are called mixed derivatives, where you first differentiate with respect to y, then with respect to x, or you differentiate with respect to x and then with respect to y. Okay. So this is very much clear. You just have to fix the value of y and differentiate this function twice with respect to the variable y. Okay. This is the limit definition. So no problem with this one. This usual way. Similarly, this is also very much clear. Here you treat this as a function of, you treat the variable x as constant and treat this as a function of the single variable y, differentiate this twice. So this is also very much clear. In terms of limit, you can define this in this way. Okay. Now, how to define this mixed order partial derivatives? So for the mixed order partial derivatives, which are these expressions with respect to xy and with respect to yx. So here you can see that first you have to differentiate with respect to x. This is derivative with respect to x. So derivative with respect to x means, and then you differentiate with respect to y. Okay, so first is derivative with respect to x and then derivative with respect to the variable y. So derivative with respect to x is denoted by fx. Okay, and then you define this derivative as the limit delta y goes to 0. Okay, so here you have the variable. When you define the second derivative, which is with respect to y, the variable x will be fixed. So you fix x naught and then change the value of y. Okay, and then take the limit. Similarly, the other type of derivative, one can define this as, the other type of derivative, one can define this as, you have the derivative with respect to the variable y and then derivative with respect to the variable x. Okay, so this will, so here you will treat this as a, this is a derivative with respect to y. Okay, and differentiate with respect to the variable x. So this here derivative with respect to, derivative is with respect to the variable x. So you fix y. So you fix y and change the value of x. Okay, so this is how these second order partial derivatives can be defined. And these are called higher order partial derivatives. Now let us consider one example on this. I have 1 minute to go, so I can finish this example in next 1 minute. So I have this function f(x,y) is equal to x cos y plus y e raised to x. So what is the derivative of this with respect to x? Derivative of this with respect to x. The first term is x cos y. With respect to x, we have to treat y as constant. So this derivative will be cos y. In the second term, y is constant. So derivative of the second term will be y e raised to x. And similarly, you can calculate the derivative with respect to the variable y by treating x as constant. Okay. Now, from this partial derivative, you can differentiate this again with respect to x. So this gives you the second order partial derivative with respect to x. So this is a function of x and y again. When you differentiate this with respect to x once more, then y is treated as constant. So derivative of this quantity will be 0, and derivative of this will be y e raised to x. Okay. Now I can find the mixed type derivatives. So first derivative with respect to x and then with respect to y. So derivative with respect to x is this one. We can differentiate this function with respect to the variable y by treating x as constant. So this will be minus sine y, and derivative of the second term will be e raised to x. Okay. Equal. These two are equal. Okay, and in the next lecture we will see what is the reason behind this equality. Okay, so I'll stop here, and if you can ask me.
Hello, class.
Good evening, sir.
Good evening, sir. Good evening. Evening.
Good evening, sir.
Good evening, sir. Very good evening. So 36 student, 37 is still coming. That's why I came a little late today.
Actually, sir, the other class is actually still going on. So that's why
Okay.
there's a delay.
So you have any question from my previous lecture?
Sir, I wanted to ask something.
Please ask.
Actually, sir, I got my hand fractured 2 weeks ago. So in my right hand, so I will not be able to write for at least 4 more months from now. So how will I write the numerical type answers? Please guide me.
Yeah, you take anyone help from your family or what can be done? I
But sir, for today, like,
yeah, I have to take one
manage.
quiz. I will take one. You take from help from anyone, doesn't matter, but you should learn. Just thinking how your baby now. Parents are feeding in the childhood, something like that.
So will there be a quiz today?
Quiz. What you have asked?
So will there be a quiz today, as you said right
Yeah, I'm
now?
planning to take. Whenever you say I will take, but I have not prepared yet anything yet.
Sir, there is a class from 5 to 6, sir. So please don't take it today, sir.
Actually, you people decide. It's not going to be very long quiz. What I give, I will ask. Submit by 10 o'clock in the night. Now don't say you have to watch the TV match, India match. Don't say all these things. I have to evaluate something. Suppose I take after 2 months, you will forget everything. Agree or not?
So then what will be there in the midterm examination?
I will be not asking again. Only one exam. That's all. It's other people duty. They would ask, but I will be not asking. I have today last lecture, and this will be over. After that, I have to take some exam to evaluate my part, and then I will be not asking any quiz. I will be not giving any question in the midterm or end term. I think there is no midterm here in this particular exam.
Sir, in the course structure, all the weightage was only of the end term exam in
Yeah,
PHN1.
that's what I'm saying. But I will not ask any question from my area in the end term. Because I have experience. Most of the people forget everything by that time.
Yeah, that's true, sir.
So we should go some better thing. I don't want to take exam ki how much you have forgotten. I just want to take exam how much basic thing you have learned, because I'm not going in a very difficult this thing. Just I want to keep simple everything. So no need to worry. I will be also asking basic questions, not more than that.
Excuse me, sir.
Please.
You are going to share slides, sir. We have not received them, sir.
Check. In fact, I forgot I have a class today. Just 3:30 I came to know I have to take one class. Truly speaking, then I immediately put my slide here and there. I prepared my lecture.
Sir, second thing is that when is quiz going to be taken place?
You will decide together.
I think what we can do is that you can give us the link to the quiz probably today itself, but you can keep the window till like around 10 o'clock or something at night.
Okay. Let us say 11 o'clock. Happy?
Yes, sir.
Sir, 12.
12, okay. 12 o'clock.
No,
But
sir.
just do
Or
yourself.
someone will say
Don't,
1 o'clock.
don't go so night. Just 12 o'clock is okay. 11:55. 12 also sometimes confusing. So 11:55 p.m. today. That's all. So I'm going to take some introductory lecture on this quantum computing. So I'm just turning off the you focus here. I think now 63 students are here. So I'm trying to keep as much as minimum. Why we need quantum computing, where is the requirement, why we are interested, how people are doing it. So little bit. So you try to understand it. So here I'm showing one slide. Commercial activities since 2014. IBM, Intel, Google, Microsoft. You must have heard all this name already. Some IDT, CQC, QCI, Northern Groupman, some all the D-Waves, all these groups are coming. Even more groups are there. I have given only the top few names. but many activities are going on all around the world, and they're working for this quantum computer, and hopefully in the market it will come. Already people have made, but in a commercial form it will come by 2050. So you are the generation who will be enjoying the quantum computer in the coming years. So far, here you can see some devices, whatever you must have seen already in your day-to-day life. USB drive, so information and physical system. So I'm saying here the information measured in a bits either 0 or 1, and information is always represented by a physical system. So all these things are some physical system. There your information is stored. Okay. Then in the bits and qubits, basically the qubit term has come from the quantum bits. I will show you. And bits, this is in a classical, it is qubits in a quantum world. So fundamental building blocks of classical computers. So here I'm talking about the bits. So we have two definite states, 0 and 1. Okay, either 0 or 1. So let us say one system is there, so it is going to be either on the 0 or it will be 1. Basically, they were applying the pulses. It's like this. So here 0, this is 1. Let us say 1, I'm saying voltage. So they are applying some voltage to get the 1, something like this. So this is in bits in the classical world. And in the quantum world, fundamental building blocks of the quantum computers, here we have a quantum bits. We call it qubits. Okay, the short form of this qubits, quantum bits, qubit. So whenever you see here, just think this is up to here, this is for quantum. All of you got it?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Okay, very good. So basic states are here 0 and 1, but one more difference is here. There is superposition. These two states, they will be in a superposition. What is the meaning of this? So suppose I make two states. This is 0 and this is 1. So it has a probability having here, having as well as having here. System can be found in the two states simultaneously. That is we calling it superposition. So here in the classical, either it will be 0 or 1. In the quantum, it will be 0, it will be 1, as well as it can be in both the states together. That is known as superposition. And that thing makes quantum world more powerful than the classical world. So you will study all these things in coming years in quantum mechanics.
Sir, but if two states can exist together, sir, then we also operate with some certainty. So if these qubits are only uncertain, then how can we operate the computer well?
The people are operating it. That
There might be
the
some
next
more.
stage, na. I'm not going, but thing is that some certainty there, na. Let us say if I'm saying this is 1 by 2, or let us say this is 1 by 4. This is beta 3. I should write in a different way. Generally, we write like this: 1 over 2 or under root 3 by 2. Basically, alpha square plus beta square should be 1. So 1 by 4 plus 3 by 4 is equal to 1. So it has a probability 1 by 4 is here and 3 by 4 is here. So where is the problem? What is the question now?
Sir, basically, I had this idea of bits of 0 or 1, like yes or no sort of.
So,
And
but here it has a possibility. Na, it is here, and always also it is here in the same time.
yes, sir. So basically,
It makes system more rich because you can do many things in parallelly. we call it parallelism. So see, right now you don't know anything, and I also don't want to go in depth, but I'm telling, I'm just giving the flavor. And once you learn the all basic quantum mechanics, then I will be able to discuss more with you people, not before that.
Okay, sir.
Okay. So quantum weight, for physicists, quantum weight, qubit, AJAY synonyms of quantum mechanical two-level system. So here I'm showing the two-level system. Generally we call it two-level system, and either it is in the here or it is in upper state, or it may be in both the states in quantum world. So in the spin, when we donate, when the atom is in the lower state, so we can also make a spin like we are showing like this. And in this case, showing downward. This is up spin, this is down spin. And for this, is a horizontally here. Just the notations people have made. So, for example, I am working in quantum optics, so we prefer this type of symbol. Those who are in NMR, they prefer this type of symbol. So, somebody, well, different, they adopt, but we know what is the meaning of this. So, when atom is in the ground state, G, I'm calling it, so we can write 0, or when in upper state we can call 1. So here I'm saying 0, 1, something like this, or we can write 0 or 1. Oh, sorry, E, excited state. We are exciting the atom from here to here. And superposition, meaning this one and this one. Just remember right now, superposition means atom in the same time, it has a probability of finding here as well as here. And probability, as I said, we are representing their alpha and beta. Alpha square plus beta square should be equal to 1. So what is quantum computing? So aim.
So can we say that using classical computers, we used to make digital signals, but quantum computers can make analog signals, something like that?
No. Analog is different. Classical is analog. Analog is different. Classical world is basically analog, either 0 or 1. Basic analog signal, we are giving the pulses. Some, let us say 0 to 5 volt. We apply, and that basically when we apply the 5 volt, then it go to the 1 upper state. Even you have a analog, just you are giving even, let us say, one waveform, but it's making 0 1 0 1, something like that. But quantum world is different. We don't use the word analog for the quantum world.
Sir, I think what she is asking is that sine wave sort of like not rigid. 0 and 1 is rigid signal, but here quantum works in probability, so the signal is more flexible.
No,
like
we don't make signal there. Alpha and beta is just a probability of finding. So how can you make a signal there?
No, like more flexible.
No. Don't mix up with anything. Alpha 0 plus beta 1 we are writing. So where signal? Nothing signal is there. Atom may be either here or atom may be here. So once you measure it here, you will find here. If you measure here, you will find it here. Only you are going to find out what is the probability. So where is the signal? You just measure the states and you find the probability of finding the atom. What is probability of finding the atom here? Probability of finding the atom here. Which signal? No signal.
Okay, sir.
And once you measure it, system collapse. That is the biggest thing in the quantum world. The moment you measure it, you have to again prepare the system. Or once you measure it, then you can also tell what is the probability of finding the in other state. Because I said alpha square plus beta square equal to 1. Either you measure this or you measure it, you will come to know what is the other probability. Okay, so aim to use quantum mechanical phenomena that have no classical counterpart for computational purposes. I said in this quantum world have no classical counterpart. So you cannot think that analog thing, whatever I was saying right now. So central research task includes whatever we do in quantum computing, in building devices with a specific behavior and design algorithms to use the behavior. We need these two things to make any quantum computing device. So mediating these two are the model of computation. So here I'm showing this one Babbage engine, silicon wafer atom. This, if you will search on the Wikipedia, Babbage engine, maybe it was made by Babbage, and I think, if I am right, near about some 1850 or something, he tried to make, but he could not complete. So it was made finally in 2002, this century, in UK. It took almost 150 years. You can find out on the net. People were trying, see, even in 1850, they were trying to find out, to do some calculation. So they were making the engine at that time. And then some devices coming with the time, making smaller and smaller. Now we are reaching to the atom's size. So it was 1 meter size. Silicon wafers, nowadays devices we are making in the, even our simple computer inside, very small devices are there. So micron size. We are reaching to the atom, the nanometer size. So basically size of the ICs is reducing, integrated circuit, whatever you call it. So there is one Moore's law. It also says that every 18 months, microprocessor double in speed, faster and smaller. So if we see the first computer was made, so let us say one IC was there, 1 by 1 inch. So let us say there was 100 circuits. Nowadays you will find 10 to the power more than 10 data of circuit in the same size, and they become more and more faster. Size is reducing, devices becoming more and more faster. So one day it will come, our this IC will be of the size of atomic size, nanometer. There is a chance, as the way we are reducing. So that's why we are reaching in the quantum world. So that's why things are coming. Future is quantum. It's better to learn in the advance what problem can happen. So here I'm showing the same, whatever Babbage engines, wafers, devices, some people are making this thing. So basically what is happening, we are saying we are making fast device, smaller, shrinking computer, smaller and smaller things we are making. So 1 meter to we are reaching the 1 nanometer. So what will happen at the atomic scale? Atomic scale, when devices will be very small. Nature does not work the way we are used to in our microscopic life. I mean, right now, you people are very familiar with the Newton's law, but you cannot apply Newton's law here. Now, even Ohm's law will also break. So that's why last 20 years, people have already started working. The moment we reach in the quantum world, Norm's law is not going to apply. Okay. So at first glance, it seems that quantum mechanics, with its uncertainty, probabilistic nature, in something to avoid when building a reliable computer. So we are doing all this study. What problem can come? What is the probability of doing all these things? So those things are going on right now around the world. Okay. So
Sir, I have a confusion.
Please.
Sir, what exactly is quantum computer? Because sir, all these uncertainties के साथ how we can operate very well a computer for our use.
See, people have already doing the measurement from last 20 years. Ion quantum gates using the trapped ion valve already made. Google has already done it. 53, they are doing it. But they showed certain algorithms are working, that probabilities are coming, some error calculations are still going on. We are in the first phase right now. Which type of error you are talking? Because when we are doing it, we know where we are putting the atom.
So we are
we have to put, suppose I want to put the atom 50-50 here, we can do it. So where is the error? Suppose I want to put alpha is equal to 1 over under root 2. Beta is equal to 1 over under root 2. So tell me where is the error? We have reached up to that precision.
Yes, sir.
Only thing is that decoherence. We are working against the nature. Some losses are there. We are doing those calculations also. Right now we are in a world. You can fix how much alpha need, how much beta you need. Either you in a Google superconducting qubit, whatever they are using, or whatever I am using here, simple neutral atom. I know per 50% exact whatever 100% correct is there information. So there is no error.
So we are starting to gain control at the nanometer scale.
Yes, already from last 20 years.
Okay, sir.
So, quantum mechanics tell us that any such system can exist in a superposition of states. So in general, the state of a quantum bit or qubit, I have already used the word for short, is described by alpha 0 plus beta 1. I have already explained what is a 0, what is 1, probability alpha and beta, finding 0 and beta and 1. And alpha, beta, these two quantities, they are complex. Okay, complex number, they have complex nature and they satisfy this equation. Okay. Superposition of states, so classical bits, 0, 1.
Sir, why complex number? Why complex number, like significance of complex numbers are not real?
When you will study the quantum mechanics, you will learn all these things.
Okay.
That's something like I am.
So aren't alpha and beta probability? So how can they be non-real numbers?
So I'm saying that when you will study all these things your second year. If you really want to study in advance, so you take quantum mechanics by Griffith, check it there. Because I am not going, that is not my part. Because then I will not reach to my aim. So today is my last lecture.
Yes, sir. One last question. What
Please.
is Feynman lectures?
You can read. You can also find there it's written complex.
Okay, sir.
Read there. Once I finish outside the classroom, we can always discuss. Okay, then I will come there. So superposition to classical bit we already have discussed 0 or 1, and here quantum world 0, 1, or it can be in both the states. So we have a way of writing it. So why I'm telling it, I tell you here. So 0, 1, 1, 0, whatever we want to write. So there is something comes register. So in the classical world, we just write 1, 0, 1. Suppose there are 3, some inputs are there, so we will be writing 1, 0, 1. But in the quantum register, we can write, so we have a three system, let us say we are taking 3 input type of thing. So we have a 2 to the power n is equal to 3. So at the same time, probability of finding it will be 3 states. Well, 4 states. I mean to the 8 to the power 3, basically 8. You can find out in 8 states. In the classical world, it will be either 0, 0 or one of this. Out of this 8, only one state will be there. But in quantum world, it will be in the same time the probability of finding in all the states. That is different here. That's why it's make quantum world very rich. So qubits have a talking. Qubit maybe visualize a unit vector on the plane. So for example, I'm writing on a, let us say this is 0, this is one type of plane. So this is alpha and this is beta, we have already seen. So basically 0 was already written. So we can see, you can make out immediately this is alpha here, this is beta here. And in general, I already said alpha beta are complex number, and if any attempt to measure the state alpha 0 plus beta 1, 0 has a probability alpha square, 1 has a probability of beta square. So after the measurement, system is in the measured state. I said just few minutes back, system collapse. Suppose I am measuring it. Yeah, if I measure it here or I measure it here, system collapse, and that will whatever measure we are in that measured state. So that is further measurement will always yield the same value. We can only extract one bit of information from the state of a qubit. So you cannot, at a time you can get only one information. And from there, from alpha square plus beta square, then you have to tell what is the other information. Both the information will not come in the same time. Another thing I wanted to tell here, if this instead of here you are here, even you have a function is this, still probability of finding in 0 you have alpha, and probability of finding in 1 beta, even this is minus here. So that thing I'm explaining here. So however, they are distinct states which behave differently in terms of how they involve. The probability is same. So have you got the point, whatever I want to say here?
Yes, sir.
Yes, sir.
Okay. So why quantum computer? These slides I got from the Microsoft I'm showing. So they were helping 2 years back for some they are using their quantum task algorithms to run some algorithms. So this I'm showing one computer. That was the first computer. It was made in, I think, 1946, University of Pennsylvania. And even you will search on the net, its name is ENIAC. You can find out first computer, ENIAC. You can see what a big size of the computer, full room is full. Nowadays you have a desktop, much smaller than this and much faster than this, whatever you're seeing here in this picture. So I'm showing you one number here. This is a 2048 numbers are there. And if you want to do the factorization of this number, suppose, as you know, okay, if you're writing 10 is equal to 2 into 5, factor of 10, I'm saying 2 into 5. So this big number is given here. It has a 2048 digit. If you want to factorize it, so simple classical computer will take 1 billion years. And if you take a quantum computer, it will take only 100 seconds. I'm just giving you some numbers how quantum computer is powerful than a classical computer. The present classical computer, they cannot factorize any number. So fastest supercomputer in the world, I have showed you in last one of the lecture in Japan somewhere, very big, same photograph. So they can study the caffeine molecule, but they cannot study the chemical molecule. So molecule is there. Even I am not expert in molecule things. So you want to, they can study this thing, but this is complex, little complicated type of molecules. Our present supercomputer cannot do all the study. So Feynman was the person who gave the idea why we should not make a quantum computer. So basically he is the father of giving the idea, not father, should I giving the idea to make a quantum computer to study the complex thing.
Sir, why only
So,
two states are there?
why?
Only two states are there.
We can do everything using two state only.
Acha, okay.
Everything can be just two state. As I said, spin up, spin down. That is more than enough. Or 0 or 1, that's all. Only thing is that one system has a 0, 1, then you can take 10 system. So here I am showing if you want to do some calculation, simple molecule, complex molecule, so some complex structure is there. Classical computer is going to take many, many long years. Even more complex, more longer year. But quantum computer is less time. So that's why I'm showing a number of atoms are more, the more longer time is going to take. The quantum computer, still whatever people have predicted so far, it's better, faster, many things come. Anything when come in the market, we always go for it is good or not. If it's good, then how much, what can be done. So all these things already happened from in 1990 to 2000. After that, people started working on it. So application, security, chemistry, materials, optimization, and all these things. So that's something. Quantum is a future. So
Sir,
I'm just showing some.
Sir, if we use more spins, I mean, if we use more than two states, sir, less spins will be needed, no?
No.
I mean, number, like...
that number need to you see one system is like this. Suppose you want to make 4 systems, then 4 will be like this. You have to entangle all of them. All game is of entanglement. The more complex system, so first we have to learn the basic system, na? Then we'll go to the complex.
Yes, sir. Okay. Got the point.
Yes, but first we have one by way. The people are already started. They are working last time. Google did with 53 qubits. But they have not done the error analysis so far. So in quantum mechanics, some polymetrics comes X, Y, Z. So in quantum computing, we call it X gate, Y gate, Z gate. So if you have a Feynman book, today you can search polymetrices. So we have one gate, we call it X gate. X be represented by this matrix 0, 1, 1, 0. So basically, if you apply alpha 0 plus beta 1 on this, the X gate is going to operate on this. Basically, when we are writing 0, it has a matrix something like this. And when we are writing 1, it has a matrix 0, 1. So when we apply X gate, so when we apply X on 0, so basically this X, this matrix has to apply on this. So you have learned the matrices multiplication, all of you?
Yes, sir.
Yes, sir.
But what will the value? Suppose you apply X on 0, X apply on 1.
0, 1.
So 0 apply on 0, if you apply on X apply on 0, what will come? 1.
Yes, sir.
Or X apply on 1, you should
Yeah,
get this 1.
it will become 0.
Correct?
Yes, sir.
So same thing I am showing here. When we have applied this X apply on this, so this become 0 and this become 1. So there is a good book, Nelson Chuang, on quantum computing. You can check it. But anyway, you will learn after coming back once you come here. And many people go for summer internship also. You can try Microsoft, IBM, whatever they call the student from here also. This is JET, polymetric JET, or JET gate we call it in quantum computing, and it has a matrix like this: 1 minus 1. So tell me what will be the value of Z0 and Z1?
One zero and
No, why only 0 will come?
0, 0 only 0.
Next.
-1 maybe.
minus
Yes.
1.
Yes, very good. So basically one phase is coming here. So many times we call it phase gate also. This is called phase gate. So when we are applying alpha 0 plus beta 1, so immediately you can see as such, because we found like this, and where 1 is here, it become minus. The phase gate. And one more very famous gate is Hadamard gate. I think I have not written the value. This Hadamard value is basically H equal to 2, 1, 1, 1 minus 1. So you check later on, because I have a limited time. So when we apply this alpha 0 plus beta 1, so in the output, we have now getting the superposition here 0 1 under root 2, 0 minus 1 under root 2 like this. You can check later on. Okay. And then very famous gate, we call it control NOT gate. So this is we call it multiple qubit gates. There will be in the previous slide it was single qubit gate. Multi-qubit gate means this we write in the short form C NOT gate. You can search on the net. Lot of information C NOT gate. So here we have two lines. We call it quantum wire A and B. So name comes here: control input, target input. So we are controlling using one from one input, the target input, and control whatever giving control, it will be always same. If you give me 0, it will be 0. Or if you give me 1, it will be 1. But in the target qubit, whatever output, here notation is like this. This thing here is plus, and here B addition modulo 2A we call it. What is the meaning of addition modulo 2? You will binary numbers if you add 0 plus 0. You must have read, I think, class 12 it has come few places. 0, 1, 1. This will be 0.
Yes.
So this is called addition modulo 2. So if I have an input and output, input I am writing in this form A, B, because A and B are my inputs. Output side A and B my decimal row A. Basically what happened when we have an input 0, 0, you have an output 0, 0. When we have an input 0, 1, what will be output?
So 1.
So zero still, I guess.
You have to write for this thing or you have to write for this thing?
0, 1, I guess.
0, 0, 1. Very good. And when we have a 1, 0, then what is output?
1, 1.
1, 1.
Very good. 1, 1. And then we have a 1, 1, then?
1, 0.
1, 0.
So what is the great thing here? Great thing here, whenever this is 1, it changes number. 0 become 1, and when you 1 here, this becomes 0. Have you got the point here?
Yes, sir.
Whenever control input is 1, target is going to be flip. Whenever control is 1, target is going to be flip. Okay. So you must have seen this famous picture. Sundar Pichai working in a laboratory. They are making their quantum computer. And this, whatever you are seeing the picture, they put almost in liquid nitrogen and it has to be dipped. So that's why a lot of energy goes here, making cool all this thing, because they have to reduce the decoherence. Okay, so I go further. So whatever I am doing it, I will tell that thing, because they are in a superconducting qubits and I am working on quantum qubits using the trapped atoms. So here I am showing one atom has been trapped. We have a technique to trap two atoms and we can increase the or decrease the separation between them. It is in our hand. Few micron to few mm, but we generally need micron distance. So why we are doing this thing? So you can see here, this on this scale, I am showing the micrometer separation between them in micrometer scale. So basically what happened, we have a technique, we can put the atom in the upper state. See, you know already atom has many states. We put the top state, we call it Rydberg state. Rydberg, I think you must have heard the name. Hydrogen, when you study hydrogen atom, Rydberg coefficient come also there. So atom, let us put in very high number, that is, let us say n is more than 50. So when they have more than 50, so atom is in very high state, it acts as a dipole. When we bring two atoms together, be very near, when they are in upper higher excited state, the two dipole interaction we can understand as a dipole interaction. So due to the dipole interaction, their interaction energy increase. So I'm just giving you one number here. You in this figure I'm showing you when they are in the ground state, what is the value here? When they are in upper state, what is the value there? So when dipole interaction take place, their interaction energy increase by 12 order of magnitude. It's a big number. And this happen only when atom is excited. If you don't excite, then there is no interaction. So that's why neutral atoms are very rich to make the atom interaction. When you can make a dipole, when you let them come out, then there will be no interaction. So when people started working initially with the first quantum gates were made using the ions, trapped ions. People already made it and they have shown a lot of result also here. So later on, when people superkinetic qubit, now working on silicon, NMR, many fields, people working everywhere. And race is going on. So other thing, whatever we call it Rydberg excitation and blockade. So generally what happens when we put atom in the Rydberg state, we cannot do with the single laser. We go in two photon case. Single laser sense what happened. Then we need a from here to here some approximately 300 nanometer light. And blue light is very tough to make and very expensive. And power is not there. So what people do, they use two laser, 780 and 480. We have a technique and we excite the atom. Once we excite the one atom, the other atom de-excite. So we call it blockade. Basically what happens, the upper state, it shifts. Now tell me you are able to understand this or not. Otherwise I have to reduce my level. I'm just saying
Not
two
exactly,
atoms
sir.
are, when one atom excite, other atom cannot be excite. If
So
two
due to
atoms are
Pauli's exclusion principle.
No. Pauli principle is different. That I said two atoms cannot be keep together. Here I am saying their energy level shifts. I have not taught this thing. You where we learn future. Whatever you have learned so far, hydrogen levels, atoms of sodium, they also shift. We call it AC Stark shift. So right now, I don't want to go in that depth. But just think, if two atoms are very near, only one of them can be excited, other cannot be excited. And that process is known as blockade. Okay. So more simple picture I am showing here. If one atom is excited, other cannot be excited. We cannot take this atom to the other upper state. And this thing, I am showing here a control and target, whatever I was showing C0 gate. That type of configuration. This process is used to make entanglement. But I am not going by only just I want to tell simple words. Suppose you excite this atom, one atom you excite, within some volume, this atom cannot be excited. Or other way, if we have trapped some atom, I'm showing you red color, some atoms are trapped. If I excite one atom, we cannot excite all these atoms within some certain volume. This we can excite, but not we cannot excite. Once we suppose we excite this, we cannot excite this, and this process is used to make the entanglement of the two atoms or more atoms. Okay, so don't think much right now. I'm just giving the flavor. C0 gate we just now saw. Okay, I'm writing a little different way. Now A and B are replaced by C and T. Or you can write same thing like this. There is also one thing we call it control jet gate. Control jet operation. So basically what happens, whenever this will be 1, it will act. When this will be 0, it will not act. Have you got the point? भाई कुछ तो बोलो, yes, no.
Yes, sir.
Okay, एक जना बोला.
Yes, sir.
Yes, sir.
So here we also apply
Yes,
0
sir.
or 1. So basically what happened, either you are applying 0 or 1, but this is going to operate only when you have a 1 here. We have seen like here, when it was 1, then target was working. So we call it control phase gate. So I just wanted to show you how it works in a laboratory. Suppose I have 2 atoms. So this is a control, this is a target. One atom is 0, other atom is 0 here. We are calling control, we are calling target. We are applying one laser pulse. Basically what happened in the quantum optics, suppose I am taking one atom from here to here. So we say we have applied the pi pulse. Or suppose I apply 2 pi, then it will atom will go here and come back. But right now, this state has nothing. I'm applying one pulse here. When nothing is there, nothing will go up. This is step 1. Then step 2, what we are doing is I'm applying 2 pi pulse here. Because nothing is here, so nothing will go from here also. Just we apply the 2 pi. Whatever I've just shown, nothing is there, nothing will go there. Step 2. Then I'm applying one pulse here back. It was here, I applied pulse here, nothing is here, nothing will come here. So you can see atom was in 0, 0. The last it is 0, 0 only. So I'm writing here input control target pi pulse on C. This I'm calling pi pulse on control, 2 pi pulse on target, and pi pulse on C. So if you see here 0, 0, 0, 0, everything is 0, 0. We started from 0, 0 and we end up 0, 0. Let us change the little configuration now. Suppose my atom is here. One is here, one is here. But remember, I am talking about control phase gate. I apply my pulse. Nothing will happen because atom is not here. Now I will apply 2 pi pulse here. So I am talking. It will go from atom will go there, then again come back. So just can you think like this? If I give the one pulse, atom will go upper state. Then again the pulse coming back, atom will again coming back by emitting one photon. That much atomic physics you already know, all of you. That's why I have kept this picture here. This is step 2. And then we are applying one pulse back. Nothing is here, nothing will come out. So if what happened here, if I write all this thing in physics term, we are only putting one e to the power I pi term here because in physics language, when atom go like this, one phase comes here. So we started 0, 1. Step 1 is 0, 1. Only when it came back, e to the power I phi 0, 1. And so on, whatever states are coming, that is minus 0, 1. Similarly, we can get for this also give minus. But if I take condition like this, both the atoms are here and here. In that case, I am applying this. What happened, I have already told, this will go up. Now, atom has reached there. The moment it is reached there, this level will shift. I have told block it. Even I excite this atom, it will not go there. Because level is shifted. It will go and come back. I mean, so if that even phase was changing, I was showing one phase change here, it will not happen. So in the last, whatever we're doing, then applying the one more pulse here, pi pulse, it will come back and it come back. And this state will obviously go back. So what happened? We are writing this result coming minus 1, 1. I will tell you soon why I'm telling you this thing. So some result has come here. Don't worry too much plus minus thing. So I just wanted to give you the flavor. If we see the theoretical result of this C control jet gate, theoretical result comes something like this. 1, 1, 1, minus 1. But when we are doing the experiments, results are coming different. So that type of cares we have to take in during the experiments. Theoretically, we are learning this, but experimentally, we are getting matrix like this. So you understand what I'm trying to say, all of you?
Yes, sir.
Yes, sir.
Yes, sir.
What is happening theory, we are not getting exactly experiment. Experimental is totally different. Results are coming. So when we are going to implement this type of quantum gates with some algorithm, so we have to take correction on all these things. So in the beginning, I said we have reached in that stage, we can measure very correctly where atom is in the system. So even theory is something else, experimental something else. So that type of correction we are doing. And for doing this thing, people now recently they have also shown some phases are coming to the ledger, and people are playing with the phase of the ledger to correct them. अभी तो atom की बात हो रही थी. Now we are talking about the layers better, because when we are applying the pulses, we are applying using the this thing using the layers. I will take 5 more minutes. Do you have any class, or should I leave here?
Yes, sir. Actually, we do have a communication skills class.
Okay, then after 5 minutes, my class became 5 minutes late, so I will go. I will just jump. Basically, I wanted to show you one more thing that is very interesting. I'm just showing here two-level atom, two-level atomic system, and any two-level atomic system, whatever alpha and beta I was showing, it has a that alpha is a function of time, and this is also a function of time. And it is e to power I omega gt and e to power I omega et. Some terms are coming there, and this is a state psi, and it is a function of time. Okay, and I can write this state anytime initial state or final state, and there is some unitary matrix. So I'm not going in details how I calculated this, but I am going to show you what result comes when we do calculation. This unitary matrix has this type of form. Okay, don't worry about this form. So what happened when we use the right values here of delta, t, omega, some values are there. Basically omega, delta depend on the frequency. We use some Rabi frequency. All these terms are there. So if we use the right value, let us say delta is equal to 0, t 0 is equal to 0. What happened? Some matrix come like this. Okay, and in this matrix, I'm going a little fast. If before I'm going to that, we have already shown this x, z. I showed you y matrix like this. We have a some rotation matrix in the quantum computing. So whatever matrix I was showing you, this matrix, if I substitute right value, this matrix I was showing, if I substitute the right value of omega or the time, so this matrix reduce to the rotation matrix, just like this in a quantum optics. So we call it rotation with respect to the x, and if I choose a value theta is equal to here pi by 2, this is nothing but x gate. So I want to say here in the nature, even we are doing simple absorption thing here, we are finding some x gate or we can get x gate or y gate, whatever we want, all depend upon which value we are giving from outside. So this is the inherent in the nature. We can make the quantum gates. Whatever they are doing is supercritic qubits in the Google quantum computer, or you are going to use the quantum computer, quantum gates using the trapped atom, trapped ions. It's inherent nature of the system. You can make the quantum gates. You are not doing any special new thing. It's already there in the nature. Only thing that you have to play with the nature. You understand what I want to say here, all of you?
Yes, sir.
Yes, sir.
So here same thing I have shown in the next slide also show if you change the some value here, so we can make the y gate. So I stop my lecture here, and you people have to tell me when should I take your simple gauge. When you will inform me, today I should take up to 12 o'clock. You have to submit the result.
Yes, sir.
Okay, sir.
So maybe then I will upload the quiz by 8:30 or 9 o'clock. Still you have 3
Yes,
hours.
sir. Please, can you make the submission time up until 12? Because I'm
11:50.
actually
I said
traveling.
11. I said 11:55 p.m. And I
Yes,
will
sir.
give the quiz.
That works, sir. That works. Thank you,
I
sir.
will give the quiz that should not take more than 15 minutes. I should not 20, let us say 20-25 minutes. Depend
Okay,
upon
sir.
you.
Thank you so much. Thank you so much. Actually, I'm
Okay.
in the airport. I'm traveling today, so that's why. Thank you, sir.
Okay. Okay.
Sir, will it
Okay.
be objective?
Pardon?
So will it be objective or a subjective quiz?
Objective though not. You have to write using your pen. Just don't use more than 2 sheets. Clear?
Yes, sir.
Okay. My lecture is over.
So, sir, you'll begin the quiz at what time again?
By 9 o'clock it will be there on the site.
Like, if possible, can you start it a little earlier? Like, if possible.
Yes, sir.
अरे
Like
मैंने अभी कुछ
6.
भी नहीं बनाया. अभी मैंने कुछ भी नहीं बनाया. मुझे बनानी पड़ेगी. मेरे को नीचे लेबोरेटरी जाना है. मेरे स्टूडेंट वेट कर रहे हैं.
जब बना दोगे तब
हाँ बस.
immediate
Don't worry.
start कर दें. Okay, sir.
ठीक है. ठीक है. Okay.
Sir, can you share the slide of
What is the
today's
syllabus?
lecture?
I will share right now immediately. बोलो कुछ पूछ
Sir,
रहा है
what
कोई
was the
जना.
theme of the quiz?
Pardon?
Sir, what was the theme of the quiz?
Simple, very simple. Whatever.
Sir, any
Simple
mathematics?
thing. No, I will not go complicated mathematics.
Sir, even today there was some mathematics, basic.
That was also not very difficult. Forget my later slide. Wherever I ask you, that was only X and Z. After that, I said complicated. I wanted to show later on mathematics came because automatically gates are coming there. We are not doing any new thing to.
Okay, fine friends, so should we start now?
Yes, sir.
Okay. So good afternoon everybody, and first of all I'm thankful to all of you for agreeing to reschedule this class. So now onwards we'll be meeting on every Monday from 5 to 6 p.m. As agreed. And so our 8 to 9 class on Friday has been permanently shifted to this slot. Well, friends, till the last class we had talked about the nature of communication, the different kinds of communication, the communication process, and then the barriers. So while talking about communication, I told you that everything communicates around us. It's not about communicating through language alone, but many a time we form opinions and impressions of things based on their locality based on the other features actually. So there are no signs or cues or languages to tell us anything, but for example, if you are traveling to a countryside and there is nobody to communicate with you, you will form your opinion about that particular locality based on its topography, geography, flora and fauna, and all other things. So you might be exhilarated to find that the air has a different feel, the sun shines brighter, and then the green fields look endless. So I mean, you can form opinion based on them as well. So mind it, while language plays a very important role in formal communication process, I also talked about non-verbal communication. Now, non-verbal communication might act independently or in tandem with language. So when we are talking, we are making a lot of use of our gestures, postures, facial expressions, and other such artifice. So they also reinforce our ideas that are being expressed. Now, this may be one of the examples of how non-verbal communication acts in tandem with verbal communication. If you recall, I told you very clearly that verbal communication is a communication involving language in any of its forms. Now, language, when we say we're talking about language in its generic sense, not in any other sense. So we are not talking about sign language or any other specific kind of language. We are talking about language that we human species speak, which is understood by a greater mass, at least in a particular locality or a particular society or a particular region. So obviously we are not talking about sign language. We are not talking about anything other than this formal language. But when we talk about formal, verbal communication, we are talking about a communication that happens through language. In any of its forms, it can be written or spoken. Now, while defining non-verbal communication, we can say that all external stimuli other than language, which helps in communication or which helps communicate something, falls under the broad rubric of non-verbal communication. Now, the most popular name of non-verbal communication is body language, but then it is not confined to our body alone. It extends to all the material artifacts, all other things that surround us. So when I was giving you an example, well, there we found that the flora and fauna and all other surroundings are communicating, even if nobody is around to physically explain us, about the place. So non-verbal communication is very broad based. So the color that you are wearing, the specs that you are wearing, the way you are grooming yourself, carrying yourself, well, your gestures, your postures, your facial expressions, your possessions, the kind of pain that you are having in your pocket. He or she is supposed to be rich. If somebody while talking has an air, people might tend to believe that he may be a big person. Somebody who is very sophisticated, polite in his or her expression would be certainly treated as a well-educated, well-groomed individual. So non-verbal communication plays a very, very important role. And now if I tell you that it plays a more important role than verbal communication, you may be surprised, because all through your life, our lives rather, we have always been told to master language in order to be able to communicate. But when we go through this discussion, we suddenly find out that non-verbal communication plays a greater role in most of communication situations. I'm just giving you an example how non-verbal plays an important role. Well, if somebody comes late to the class and the teacher asks this question, why did you get delayed to the class? Well, and the person says, sir, I'm sorry, I got delayed. Well, there is another person who comes late and the same question is repeated, and he or she says nothing with downcast eyes, accepts the mistake. Now, if I ask you which of the two ways communicates more meaning or looks appropriate, can you tell me the first one or the second one? Second one. Second. Well, so does not this convince us that non-verbal is more effective compared to verbal sometimes? Because maybe the spoken words are I'm sorry, but then your body says something else. So by not reinforcing whatever you are saying with an appropriate bodily gesture, you are making fun of saying sorry. In fact, you don't look sorry. But in the second instance, the person says nothing, but still the whole body joins in saying sorry. And that's why it is so effective. So many a time you will find that, but yeah, let me tell you one thing. There are different cultures, and so the interpretations of body language are as different. When we talk about something being conveyed through an object, then also we have to be aware of the cultural differences. Why? Because the colors may have different signification in different cultures. Likewise, different kinds of symbols might communicate differently in different circumstances, and we'll look at that. So friends, we are going to discuss non-verbal communication, and you will be surprised to know that it forms more than 90% of your communication, especially in face-to-face communication situations. And if your body language is not proper, mostly your communications are not effective, or they are not able to create the same kind of impression that you intend to create, or they are not able to fetch you the same rewards that you expect them to do. I can just give you n number of examples from my own experience where I have seen that effective communication. When I say effective communication, I am talking about somebody who is capable of combining both verbal and non-verbal appropriately. So when we see the great actors delivering some dialogue, and the same dialogue is given to a novice or a third class actor, we find that they fail to do justice, while the great actor creates an aura out of it. And how does it happen? It happens because the spoken words are appropriately backed up by non-verbal communication. So the body language, the voice modulation, the facial expression, the articulation, the bodily gestures and postures, the pauses and inflections, they're all top quality. So friends, I mean, this really matters. If you know how to take care of your body language, you can create impression. Well, when I talk about the body language of IITians, I can tell you for sure that they are not one of the best dressed people. When we look around, we find our students very careless and very casually dressed otherwise. But when the placement season comes, we are not able to recognize them because they're completely changed and they start looking like pros, professionals from top to bottom. And even otherwise also, whatever may be their dress, they're always bright and beaming with confidence. And that really helps the way they talk and approach people. So, I mean, so that is the power of body language. So friends, we are going to talk about it with the help of some slides. And once I have finished, I'll again share these slides. I had already posted the other slides of process and barriers. Hope you have got it. So, did you get these slides?
Yes, sir. Yes,
sir.
Okay.
Yes.
So let me see. It's sharing. So once it shares, then we can. Sometimes it is stuck up. I don't know. So are the slides visible? No. Not till now?
Yes, sir.
They are visible.
It is visible, sir.
Visible, sir.
It's visible. Okay.
It is visible.
Okay.
Yeah, sir, it is visible.
It is visible.
The
Hello.
slides are freeze.
Hello, sir.
Yes, slides are visible.
No, sir. Now it's not visible.
No,
No, sir.
Okay, in between I lost my connection. Actually, sometimes sharing is difficult because it gets stuck up. So it stuck up, and so I'm again trying to share it.
So
Yes,
now
I
it's
have to be, yeah, I have to be able to move it also. That's the problem. Because I'm not able to see it. Is it visible to you?
Yes, sir.
Yes, sir.
Yes, sir.
It's visible to you, but it's not visible to me. And unless it is visible to me, I cannot move it, I guess. So let me try. Is it moving?
Yes, sir. Yes, sir.
Yes.
Yes, sir. Yes,
Can you see the second slide?
Yes, sir. We
yes,
can
sir.
see.
Yes, sir.
Okay. Okay, fine, friends. We are beginning with a couple of quotes. One is almost a proverbial quote, which says, "Actions speak louder than words." So we might love people who talk a lot, but we might love those people more who talk less but do more. Am I right?
Yes, sir.
So just talking about something does not make much of a difference unless and until we also act. Fine. And in the same connection, heard melodies are sweet, but those unheard are sweeter. This is another beautiful quote to begin with this. Let us come to this. There is a cultural critic whose name is Edward T. Hall. Now, Edward T. Hall has contributed significantly to the study of non-verbal communication. And then there is another one whose name is Mehrabian. And these two names are very, very important. And the studies that they have conducted, they reveal that 60% of all human communication is our body language and 30% is tone. So hence 90% of what you are trying to tell is not coming out of your mouth. It is coming from somewhere else. So as a result, any body movement, posture or material artifact which encodes or influences the concept, motivation or mood is neither matter nor energy but information. So simply put,